In this video, I'm going to look at a recent electrochemical exam question. Invariably, the questions that turn up in exam papers seem a huge amount more complicated than the ones we get in our textbooks. They're using unfamiliar half equations, and they tend to choose ones that are as confusing as possible. Vanadium features heavily in exam questions, and you'll see why shortly. So we have a vanadium battery using a half cell containing V2 and V3 plus ions. So those are both in the same half cell. And another half cell containing VO2 plus and VO2 plus. You can see how confusing this is going to become. We've got some electrochemical data. We've got a student who is going to find the E cell value for this electrochemical cell. So first of all, we need to be clear which half reactions are involved. We need a half cell that contains both V3 plus and V2 plus. So that would be that one there. And another half cell containing VO2 plus and VO2 plus, which would be this half cell here. So these are the two half cells that are involved in this particular battery. So question 1, draw a labelled diagram of the apparatus the student uses to set up this E cell. This is worth 4 marks, and it's worth doing this correctly. What are the things that they're looking for? Well, first of all, we need the right equipment. So we are going to need a high resistance voltmeter. It is going to be connected to electrodes. Okay. I'll draw my electrodes like so, because if we look at the two half cells involved, we've only got ions, which means that the electron transfer is going to have to take place against an inert electrode, and inert electrodes are invariably platinum. So I would indicate that I know that I've got a platinum electrode in each half cell. They need to be in contact with the solutions of ions. So I'm going to put in my beakers. And we can see here our solution. Make sure that your electrodes actually go into the solution. Make sure that your wires are actually attached to your electrode. Leaving little gaps, being a bit slapdash is where people lose marks very easily. And let's not forget that I'm going to need a salt bridge to complete my electrical connection. So I'm going to label that. If I go back to my half equation, my oxidation half cell is the one with the less positive standard electrode potential, so I know that needs to go on the left. So in my left-hand beaker, I am going to have V3 plus ions and V2 plus ions. They're both in solution. My reduction half cell with the more positive standard electrode potential is this one here at the bottom. So I have got all sorts of things in here. VO, and you need to write this carefully, you can see why they choose these, VO2 plus. Hydrogen ions, clearly this half reaction only takes place under acidic conditions. And my VO2 plus ions, and these are all aqueous. I squeeze in my state symbols. So what is the examiner looking for? High resistance voltmeter, salt bridge, platinum electrodes, that I have the ions, the correct ions, including the hydrogen ions in my solution. And they will also be looking to check that your wires are actually in contact with your electrode, that your electrode and your salt bridge is actually in contact with the solution in your beaker. So these are the little things that can very rapidly add up to you not getting the marks that you deserve. Part 2. Use the data in the table to calculate a value for this E cell. Okay, so I'm going to remind myself that E cell is always the standard electrode potential of the more positive or the reduction half cell, take away that of the less positive or the oxidation half cell. If I go back to my table, I can see that the more positive is the VO2 plus 2H plus half cell, and the less positive is the V3 plus V2 plus. So we have got and obviously you don't need to write all this out each time, but I want to make it really clear what my thinking is. H plus VO2 plus, that was the more positive, take away the less positive. So that is going to be plus 1.00, take away the less positive, which is minus 0.26, and plug that into your calculator, and that comes out to be 1.26 volts. And having done all the working and come up with the correct answer, let's not forget to actually write the correct answer into the answer space. Part 3. Give 2 reasons, other than experimental error, why the E cell value that the student measures is different from that calculated above. So we need to go back to the details of the experiment. The student works at room temperature, which is about 20 degrees C, and uses approximately 0.1 mole per decimeter cubed solutions. So this student is not working under standard conditions. However, you will get no marks for writing the student was not working under standard conditions, or the experiment was not calculated or carried out under standard conditions. We need to be more precise than that. So, reason number 1, the temperature was not 298 K, which is 25 degrees C. It was approximately 20 degrees C. Number 2, under standard conditions, we'd expect the concentration of everything involved. So that's the V3 plus, V2 plus, the VO2 plus, the VO2 plus, the H plus to be 1 mole per decimeter cubed, and they weren't. They were approximately 0.1 mole per decimeter cubed. So we can say concentrations, we've got a couple of points we can make here, of the ions were not 1.00 mole per decimeter cubed. We also know that the concentrations were not exactly equal. If we look back to what the students did, they used concentrations of approximately 0.1 mole per decimeter cubed. Why would that have an effect? Well, if I were to take just the first half cell, V3 plus plus an electron go to form V2 plus. If they weren't exactly the same, let's say that I had measured out approximately 20 centimeters cubed. I didn't use a volumetric pipette. And so the concentration of that was about 0.1 mole per decimeter cubed. But because I hadn't made up my solutions particularly accurately and not used a very precise way of taking the volume of V3 plus, say that was about 0.13 mole per decimeter cubed. They're both approximately 0.1. This is an equilibrium reaction. So the fact that I have a slightly higher concentration of V3 plus means that the position of equilibrium is going to shift to the right. As a result of that, electrons are going to be removed from the system as they react with the V3 plus ions to form V2 plus ions. If we're removing electrons from the system, then I know that the electrode potential is going to be more positive. Or rather, I should be saying that the electrode potential will be more positive than the standard. Would be a better way of writing that if I were to give a better or more full explanation. Part 4, write an ionic equation for the reaction taking place when it's producing a current. So this is when we've removed our high resistance voltmeter and we're allowing electrons to flow from our oxidation half cell to our reduction half cell. So I can look up my two equations, V3 plus an electron to V2 plus and VO2 plus 2H plus an electron going to form VO2 plus H2O. You can see how students who are in a hurry made errors here. So my oxidation half cell was the one with the less positive standard electrode potential. So I know that V2 plus is going to be oxidized to V3 plus and VO2 plus is going to be reduced to VO2 plus. The electrons already balance. I've got one electron in each half reaction. So I just need to put my reactants on the left-hand side and my products on the right. So I'm going to have V2 plus VO2 plus 2H plus going to form V3 plus VO2 plus H2O. And finally we come to part 5. So the student was going to use a solution of sodium iodide in the salt bridge. However, having considered the data, they decide that the sodium iodide react with one of the vanadium ions. Which vanadium ion, why, and we need an equation. First of all, let's be very clear that sodium iodide, the sodium is a spectator ion. So what we're interested in are finding a vanadium ion that's going to react with iodide ions. So let's go back to our data. The half equation for the iodide ions, we've got iodine picking up 2 electrons to form iodide ions. If the iodide ions are a reactant, then that has got to be the oxidation half cell, which means that iodide ions are only going to react with vanadium ions that have a more positive standard electrode potential. So I've only got one option here, which makes it quite a straightforward question. They can only react with VO2 plus, because VO2 plus is the only half reaction that has got a more positive standard electrode potential and would be happy to be the reduction half cell in this setup. So I can place my answer here. It's going to be VO2 plus, being careful to write that so I get the correct ion. My reasoning is because it's the only ion that has, so VO2 plus H plus VO2 plus half cell has a more positive standard electrode potential, or I could write E with the bus stop sign. So would be the reduction half cell when combined with the iodine 2I minus half cell. Now, I'm being very careful or cautious with my language here. This is a really common error with students. They're in a rush and they don't think through exactly what they're saying. So I often see writing such as vanadium is more positive. Well, that's a complete load of rubbish. It's the VO2 plus H plus / VO2 plus half cell that has a more positive standard electrode potential. It itself isn't more positive. It's the standard electrode potential that is more positive. So you need to learn these little phrases and make sure that your answer actually says what you're trying to say. It's a classic case of me reading student answers, and I know that the student knows what they're talking about, but actually what they've written on the page makes no sense whatsoever. And then finally, our equation. I'm going to need to double my vanadium half reaction. Let's have a look at why. Where's my data table? Here it is. Okay, so this half reaction's only got one electron, whereas the iodine half reaction has two. So when I write my full equation, I'm going to have to multiply that one by 2, which brings me to my final answer of 2I minus, because this is the oxidation half cell, plus 2VO2 plus 4H plus goes to form, they don't give you much space, do they? VO2 plus I2 plus 2H2O. Done.